But so I would probably increase the learning rate, and then if that got worse, then I would say I probably was in a weird situation like this, and then I would, yeah, and then actually decrease it, and you're going to be closer to the target. It's not uncommon to do some guess and check as a starting point. Okay, so any questions about this? Great. Let's okay, so fitting a model to data. So now we're going to start with data x, y, right? Which is okay, and in general, xi would be in RD and yi r. So we're going to talk about linear regression. Although this would be a similar thing we can do for classification, and maybe you can do this for clustering or dimensional reduction. Although we'll see there are other techniques there which we'll use. Those problems aren't convex, but there are other ways to solve them. Okay, and then so what we want is going to be some model M alpha, right? And again, this model is going to go from RD to R, and you want to think that M alpha of xi is going to give you yi hat, which is the approximation of your yi. Okay, and in order to do this, we're going to have what's called a loss function, which will generalize this in the classification section. But for now, so we're just going to, in general, define a loss function, which is going to takes in xy and m alpha. And in general, we're going to use, and so basically we're going to set this function equals to f of alpha. Okay, this is, so basically the loss function, and I'll write down an example of the loss function, but this takes in the data and the knowledge of however I build a model. The model has parameters alpha, and now we're going to write this as a function of alpha in some way. And so the loss function will say will typically be the sum of the squares loss function, which is going to be equal. Let's write it this way. So the sum over all the data points, the model applied to xi minus yi squared. Okay, so this is a choice of the loss function. This is the sum of the squares loss function. And we're setting, remember, we're setting this equals to f alpha. Alpha shows up in the model here. Okay, or it might be, yeah. Okay, so this gives us a function f alpha, it seems, okay, it seems reasonable, and now these alphas are the values we want to find that minimum. We want to find the choice of alpha that minimizes this cost function. Remember, for linear regression, we had a closed form solution for this, but we're not going to use the closed form solution here. We're going to use gradient descent. So if we wanted to, we could add some embellishments on here. If you look in the book, in the linear regression section, there's all the stuff about adding regularization term on here. For instance, with the lasso regularization term, it keeps it convex, and so this is a common thing to do here as well. We'll also talk about there's ways you can make this more scalable, and we'll get to that inside this lecture. Okay, but I haven't, let's make this more concrete, and let's specify the model here. And in this case, I'm going to consider the model when we're doing quadratic regression. Okay, and so that means that this model is going to look like alpha 0 plus alpha 1 plus alpha 2 xi squared. Okay, we'll use this model as an example. It's basically the simplest thing that captures all the complexity of what's going on here. And so now this means that alpha is going to be alpha 0, alpha 1, alpha 2, and so d is going to be equal to 3 here, right? Not that d, but d in terms of the function value. This d was d prime for consistency. Okay. And d prime is 1 in this case. Okay. But we've done this linearization of this model, so we can now get these 3 parameters. If I wanted to do cubic regression, I'd need another term here, or quartic. I'd need a 4th term. If I had 2-dimensional xi, right, then I would expand this in multiple ways. I'd have 2 linear coefficients, 1 constant, and then I'd have 3 quadratic terms, right? So if I have if xi equals, I'm using y for something else, but if it's pi qi, right? So this is 2 dimensions are 2, and 2 equals d prime here. Then the model f alpha xi would be alpha 0, alpha 1, pi plus alpha 2 qi. This is constant term, these linear terms, plus alpha 3 pi squared plus alpha 4 qi squared plus alpha 5 pi qi. Okay, and if I wanted to go cubic, I would expand this, and I would have a bunch of cubic terms here as well. All right, so let's focus on this model here. Okay, and so the key step here is going to be defining the gradient now of f alpha, and so I want to calculate this. And I'm going to show you for like any model like this where it's essentially some dot product model, there's going to be kind of some common form that is going to show up here. And I'm going to say when f of alpha equals f1 of alpha, meaning that that there's only n equals 1. So and equals 1 data point. Let me write it out for this case first. Okay, so there's going to be 1 data point. That's going to mean that x, y is going to be equals exactly the set x1, y1. There's only 1 data point. We'll write out the function in this case, and then we'll say, okay, there are a bunch of them, so I take a sum. Okay, so it's going to be a simple extension, but let me just write it out for this first case first. It'll be it's going to make stuff simpler to write up on the board. Okay, and so now that means this f of alpha function equals f1 of alpha is just going to be alpha 0 plus alpha 1 x1 plus alpha 2 x1 squared minus y1 squared. All right, so this is my whole function now. And remember, it's in terms of alpha, x1, x1 squared, and y1. Just x1 and y1 are given to me. These are constants. But to write the gradient, I need to do the partial derivatives in terms of alpha 0, alpha 1, and alpha 2. No, it's not going to be hard. But let me just go through this. So in general, d of d alpha j, where j equals 0, 1, or 2, right? This is going to be equal to is this. And so before I expand this, I want to actually, I've got this, it's this term squared, so I want to actually do the functional derivative here, which is going to mean it's going to be 2 times m alpha x1 y1 times d alpha j of m alpha x1 minus y1 squared. Okay, so I'm going to factor this out first. Then this form is, let's move it over to here. So if I expand this form out, 2 of m alpha x1 minus y1 squared times d of d alpha j, and then if I can write this as the sum of j equals 0 up to 2 alpha j x1 to the power j minus yi squared. Okay, so this is writing out the model. All the models have some form that's kind of like this, right? Any polynomial of one-dimensional variable will look exactly like this up to the polynomial p. This is for all j. If I do multi-dimensional or linear, it's a little bit different, but it essentially looks in this form. And it's basically sum over all the coefficients, but I'm only taking the partial derivative with respect to alpha j of this form. Oh, wait, this is not squared up here anymore. Okay, which means that the partial derivative here, this part comes down. This term, the partial derivative with respect to alpha j, I've got j inside of, this is a j prime, I guess. Okay, it's just the jth term, which is just c of I to the power j. Okay, only when the j's match is this interesting. This term is a constant. All the terms which are not this j term here are going to be constants as well. So, and then the xi to the power j is a constant, and so that differentiates in front. Okay, so that's it, and that means that is going to be d of d alpha 0 right? So this is the definition of the gradient, the partial derivatives of the 0th, 1st, and 2nd one. Yep.
Sorry, just like to zoom out. I guess the goal here is to replace that like matrix conversion definition closed form that we had at the end of the linear regression chapter. Is that right? To find a model, or I guess.
Yeah, sure. You can replace it. It's another way of calculating it. It turns out this is a more commonly used way to calculate linear regression, and we'll see a scalable version of this next. Okay, the scalable version is actually what's used with really large data sets, and this is more generalizable. The linear regression model is, it has a closed form solution, but a lot of other things you'll see throughout a life as a data scientist will not have a closed form solution, and this will be a little bit more complicated, but not that much more complicated. Okay, and so basically, I can write, this is going to be 2 times and then I can, this term fact, it's the same in all of these guys, and then this will be the vector x1 to the 0, x1 to the 1st power, which is nothing, and x1 squared. Okay, so the gradient, okay, so the point of this derivation, which hopefully wasn't too hard, maybe it's a little refresher for you, is that the gradient with anything that looks like a kind of this, this dot product sort of model ends up being 2, which doesn't matter so much. This can factor in the learning rate, whatever. The error, the model minus the minus what the prediction is, right? This is the residual, the size of the residual. So the larger the residual, the larger the gradient, times the actual function values here. After they've have been linearized, where this one, this term is actually 1 x1 and x1 squared, right? So I have to calculate the actual error I get at this data point once, and then I multiply it by basically the actual coordinates of the data point, which are fixed. Okay, so to calculate the gradient, I just need to evaluate the model. And this will be true basically, and then write out the expansion, right? So I have to evaluate the model, which involved doing this. But so anything which is in your higher dimensional version of linear regression or any sort of polynomial regression, or any other thing that you can do some expansion like this, I just evaluate the model, I subtract it, I multiply that by the expansion, right? So the gradient is really simple to calculate. This is known in general as the Widrow-Huff so learning rule. Okay, so for this case, the gradient is actually pretty simple. Okay, so this means, and what's really useful about this is that, so the gradient, right, is proportional to the residual error. Right? If the residual error is large, then the gradient is going to be large. If the error is small, the gradient is going to be small. Right? So if you remember, my stopping condition that I wanted to use was going to be based on the norm of the gradient. This part is going to be fixed for any data set I'm using. The 2 is fixed, right? And so it only depends on the norm. right? So in this case, I'm actually, my stopping condition is in some way kind of related to the norm. I guess in any linear regression sort of model, it's actually proportional to the norm of the residuals. Okay, or these could cancel out if I'm summing up a bunch of terms too. So it's not just the norm of the residuals. Notice this could be negative as well. So if I'm adding up things, these could cancel, right? But so it's a little bit different than the norm of the residuals. But if they cancel, so I can't do anything about them, then it's gonna help me factor that into knowing if I'm slowing down because I'm getting close to the optimal solution. All right, so there's this really convenient form for the gradient for these sorts of problems. Okay, so hopefully taking the derivatives here kind of functionally is not anything surprising. And hopefully walking through this version gives you kind of an intuition of how stuff is working. Okay, so the next point that's important to make is that, and this is also when you're using the sum of squared errors. Another reason why this is a really convenient form. For sum of squared errors, this works out. If it was sum of cubed errors or something like that, then I wouldn't quite be able to do this. It'd be more complicated than just factoring this out. I would get that square should be there. Okay. It would be that this would, if I just factored one term out, if it was cubed, then there'd still be a squared left up here, right? And that squared term that was left, I'd have to do this again, and so it wouldn't be so simple. So sum of squared errors again happens to be very nice. Okay, so the next important thing to get out of this is that these functions for fitting this model to data are what's called decomposable functions. Okay, so my f of alpha is going to be equal to the sum equals x I y I of f of I alpha. Okay, where f of I of alpha, in general, this could be equal to some loss function on here. So this is right in blue, so it red, so it stands out here. There's some loss function which could be this. Usually, it's the squared loss for our examples in this class, but in other cases, it'll be a different loss. So the point is that this function is going to be the sum of these functions. Okay. Blue marker. Okay. So this is going to have two important implications. Okay, so I've described how to compute. We can, so this is going to lead, let's say there are going to be two important algorithms that come out of this. So batch, so batch gradient descent will be that I can also write the gradient f of alpha is also going to be the sum over I of the gradient of fi of alpha. Okay, and so this I can then, for for squared error, here I can use the the Woodrow-Huff rule, which I detailed over there, right? So if I have the sum of squared errors and I have one of these dot product-based models, then each of these terms for each fi I can compute very simply by just doing a function evaluation. And I just take the sum of them to get the full gradient here. Okay, and so batch gradient descent is just using this, right? So in order to compute the gradient. Okay, what's nice about this is I know that f of I of each of these f of I functions is going to be convex, because this function is going to be quadratic, right? It's a linear in all of the alpha terms, because this one is multiplied by 1, and x1 and x1 squared are constants, and y1 is a constant. Okay, so, and it's taking squared, so this is a quadratic. It's going to be convex, which means that f equals the sum of fi is also going to be convex. So as long as my loss function L is convex, is a convex function of this, then the sum of them is also going to be convex. Okay, what I don't have yet is that I want to say it's strongly convex. And I do not have, this is not strongly convex. This one is not strongly convex. Each of the f of I functions is not strongly convex. Okay, so let me try and draw a picture here. Okay, so what's happening, let me try and draw the picture for like linear regression. And what's going to happen with linear regression is I'm first going to draw, this is x1 and this is y1. And so I'm going to have one data point. I have one data point. And so, right, so F1, right, so that means that if I fit a line through here, if this line is equal to this model F alpha, this means f of alpha equals 0, because it goes right through this data point. Okay? But this line does too. L prime, right? I'm also going to have f of alpha prime equals to 0. And in fact, that's going to be true for any line that goes through this data point. Okay, what's happening is that I can look at another picture here. Alpha 1, alpha 2. Right? This is in the space of the alphas. And it's going to turn out that there is some, maybe I should write this in red. Okay, now this function is this like a dual space. So this will correspond to a single model here. and alpha. And then there's also going to be this other model, m alpha prime, which is, both of these are going to have function value 0. The trump, there's going to be this one-dimensional subspace where the function value is going to be 0 along here. And you're going to have a quadratic function. This is going to be f1 of alpha. So if alpha is along this line, the function value will be 0 for f1. But if it's off here, it goes up so quadratic. Okay, and it turns out that it's going to be the one where the dot product with 1 x1. If the dot product with this vector is 0, then the cost is going to be 0. That's why it's a line in here. Okay, so what happens? And so what's going to happen if I have a quadratic fitting function instead? I don't just have all the lines count as sub-quadratic functions where alpha 2 is 0. So that means I still have this problem, but now I have also the choice of alpha 2. I can pick that as something, and I can still go through here. So that means in this space, which is now 3-dimensional, I'm going to have a 2-dimensional subspace of things which are all 0. So it gets even a bigger subspace of things which cause it to be not strongly convex, right? This function is convex, but it's not strongly convex because it's got this kind of locus of points which are all the minimum, right? And in the direction along here, I can't lower bound it with some sort of quadratic function. Okay, the good thing now is that if I add another point here, let's do another point down here. This is x2, and this is y2. Right, so this is the second point. Now, this function L with m alpha still has a cost of 0. There's one function that's going to have a cost of 0, but this other one, m alpha prime, is not going to have a cost of 0 anymore. This is good. And in general, what this means is that now I'm going to have a second kind of function through here, right? This is going to correspond, this is going to have a different dot product. Now, this is the normal direction to 1 and x2, or maybe this is 1 minus, we got a factor of 1 minus y1, y2, 1 minus y2. Okay. Okay, a different set of curves that have, all of these guys are also going to have for f2. This is now corresponds to f2, and so f2 is 0 along this line here, and right where they meet is going to be at m alpha, at the alpha which corresponds with this line here. Okay, so if I add together a bunch of weakly convex functions that are not strongly convex, they're probably going to be convex. And in general, this will be true if the data points are full rank. Okay, so if basically x, y is full rank, then you're going to have f is going to be convex. It's going to be strongly convex. And full rank, it means full rank in terms of I have to do the polynomial expansions in this way. That using y and x1 and x1 squared and so forth. So in higher dimensional models, I need those. I'm in higher dimensional space, and those points need to be full rank in this space if I write them as a matrix. Then f will be strongly convex. So now I get strong convexity, and I'm going to have this faster convergence rate. If I don't have this full ring condition, then there's going to be a multitude, a continuous set of models which all give me zero error, or the same error at least, and that leads to its underdefined system, and you get these other issues. And there are other ways to fix it, which you'll see in the data mining class if you take that. But it's kind of, if you have enough data for your model, then it should be strongly convex, generally.
Can we see an example where there's a model with alpha and model with alpha prime? I'm confused because I want to know if will it have the same format of alpha 0 plus alpha 1x I plus alpha 2xi squared?
Oh, so if we, so you're saying for the quadratic version? No, what was that? So in the,
I want to know how to distinguish like L and L prime.
L and L, these here.
Yeah.
Yeah, so these are, this is just a linear model, so the model is a line, right? And I'm measuring the error in the y-coordinate, right? So this is, this line here, right? I'd write this, this is the offset, alpha 0, and the slope, the rise over run, corresponds with alpha 1, right? So this line is equal to alpha 0 plus alpha 1 x1, right? It's that y is equal to this for the model times x in general for any x, right? So these are all the points that satisfy this equation. And if I choose a different alpha 0, alpha 1, I get a different line. I can choose a different line that goes through the same point. Right? So there are this infinite set of these lines, and those correspond with an infinite set of models that for this one, I guess this one data point give me cost of 0. But if I add another point, then there are no longer an infinite set of models that do this. So that means combine these together, I get a strongly convex function, and I get this great convergence properties here.
So is it accurate to say that this whole practice was just to prove that m of alpha as a function, or sorry, m alpha, the model as a function of alpha is probably strongly convex.
For f. For f is probably strongly convex.
Okay.
Not fi. Fi will be convex, but will not be strongly convex. That's just one of these kind of half pipes here. Each fi is one of the half pipes. But if I take the average of two half pipes, it's going to be strongly convex. This is going to give me a single polynomial where this is the only point that has 0 error. And I add more and more half pipes onto here, all different directions, then I'm going to get it's not going to give me this kind of, it's not going to give me like a really radical surf park, skate park. It's going to give me just a single quadratic, which is going to be boring from a skater's perspective, but from for gradient descent, it's great. There's going to be a single minimum. It's going to get this really fast convergence. Yeah.
So the motivation for this is doing what we did over on that board, but with like multiple data points,
right. This was, I just went through it for one data point. Now I say, if I have multiple data points, I just add these functions together. It means I can just add their gradients together. And generally, if the data is not ill-conditioned in some way, it's going to be strongly convex.
So I think I'm missing the link. If we have multiple data points, why does that result in an f that we need to break, like a loss function that we need to break up? Like, what is the motivation behind that?
They typically are decomposable, right? We typically model the cost function, sum of squared errors. That's the sum of squared errors is decomposable in that I can write the full sum of squared errors in terms of a sum over all each data point only affects one function, one fi. This corresponds kind of like with this independence assumption we saw in the Bayesian inference part of the course, where I assume the data points are independent, so I can take their product, and then their log of the product is a sum. Right? So it's the same sort of thing going on here, and so this is a very common assumption that every observation we have independently affects my total error. And that means my function is decomposable. And so one thing it allows me to do is to write my batch gradient descent as the sum of individual gradients, which are easy to compute, and they're going to add together to give me something strongly convex. This is batch gradient descent. Okay. Okay, so batch gradient descent means that after like log 1 over epsilon steps, I've got an epsilon error. It means roughly every constant number of steps I take, I resolve 1 digit of precision in my answer, which is great. The problem is that every time we compute the gradient, I need to look at all of my data. And so if my data is big, then it takes a long time to compute every gradient. All right? So that part is not good. So if I'm training on, training on something like ImageNet or one of these huge corpus text, one of these big data sets I have of, if you're training on all of the movies people have ever watched on Netflix or recommendation system, every time I take a gradient step, I don't want to go and read through all that data and do even a function evaluation for every single one of those data points. Right, to do the gradient, I just need to do the function evaluation, but I don't want to do it for every single one of my data points. That's going to take a while. Okay, so the second thing I can do with decomposable functions are what's called these stochastic or these incremental gradient descent. Oh, so let me just write this out. This was still in batch. Then I think it's worth writing this out. Here is that this will just kind of going through all the steps. This will have this form of m alpha of xi minus yi times 1 xi squared. Right, so the batch gradient looks like this. I've got this sum over I equals 1 to n. So I just need to do the function evaluation with whatever current value of my model is. And then so this is, but I have to do this for all n data points. If n is big, then this is slow. Okay, so this is typically not what's used in modern large-scale machine learning. 15 years ago, this is what everyone used because data wasn't so big. Now this is not what's used. Okay, so instead we do stochastic or incremental gradient descent. And so you might have heard this called just SGD, and there are lots of variants of this out there now. So this is stochastic gradient descent, and this is commonly what's used. Let's start with the with the incremental version. And so for incremental gradient descent, okay, so I'm going to start with alpha 0 at alpha init, sure, and then I'm going to repeat alpha k plus 1 equals alpha of k minus gamma of k and then return alpha k. Okay, so this is like gradient descent. The main difference here is that now I'm only going to use the gradient using just one of the data points. And so I'm going to kind of cycle through these. Let me say initially alpha I equals 1, right? So I'm going to start with I equals 1, and I'm going to cycle through the data points and take probably a smaller step than I did before. So the learning rate will probably be smaller than before. But it's not going to be smaller by a factor n. It might be smaller by like a factor of, might be square root n or something like that. Smaller. So I don't need to look necessarily, if I have lots and lots of data, and especially if my model is small, then I can look at just a few of these, and I can look at just one and take one step, right? So I'm just gonna, I have a bunch of these different cost functions. If my model is out here, right? So if I'm starting with alpha of k out here, if I look at either of these cost functions, either I'm going to move this direction or this direction, but I'm kind of going in the right spot. I'm kind of going towards here where the minimum is going to be. And so if I have lots of data and it really does come from the model I want, this is kind of going to work the way I want it. And I probably don't want to take as big of a step because each gradient, think of this as an estimation of the gradient. It's going to be noisier. But if I take smaller steps, then on average, the steps are going to get me in the right direction. Okay, so it's hard to prove something about the incremental version. The stochastic version is instead going to do this same as before, but now I'm going to choose I from the set n at random, and then I'm going to do my update. I don't know if you can see that. Okay, but basically the difference with stochastic gradient descent is that instead of just cycling through them in order, then I'm going to choose one of the data points at random every step. Okay, so stochastic gradient descent is the one that you can prove stuff about. Incremental one is what people typically use. If they want to be maybe a little bit safer, they'll randomize the order of the data and then they'll cycle through it. But if you're assuming all your data points are independent and they're IID from a random distribution, then these are almost equivalent. This one doesn't use anything twice. This one might use something twice. So, typically people will analyze stochastic gradient descent, and they may call this stochastic gradient descent, even though technically it's incremental gradient descent. But this one, you can prove stuff about it in that if your step sizes are not too big, that kind of looking at a bunch of steps, not necessarily all n of them, but some number that depends on d. Like if you took roughly, let's say, d squared steps for a d-dimensional model, then on average, those are going to look like one step, close enough to one step from the full data. And I'm not going to go into the analysis of how this works, but you can kind of imagine by some concentration of measure. I could have instead done something where I said, let's grab a bunch, let's grab m points, m data points, estimate the gradient from those m data points, and then take a step. Turns out it's better to look at them and take a little step every one at a time. You get kind of more improvement as you go. So people use this typically instead of taking m all at once. Okay, and so this means that, so if your data is really, really big, you will probably converge before you look at all of the data. Although you could keep training, right? If you have not converged, you can go and cycle through the data another time. That's why I have this mod ending. Right? So I could cycle through the data 2 or 3 times. So if my data is not too big, I can still run this, and I can cycle through it 2 or 3 times until I converge, if it's a complex problem.
So with these methods, your like path might go like completely random places in the like big loss function. Even though it's convex, you're not necessarily going down each time. You're
That's
hoping
correct.
that eventually you'll make it down.
Yeah, you're not necessarily going down every step. That's true. You're going down with respect to the loss function that you considered, right? But you're not going down with respect to, which is just defined by one data point, but you're not going down with respect, necessarily with respect to all the data points. So generally, if you start with your model far away from the optimum, and your data is actually, there is a model which fits the data pretty well, then most of the data points are actually going to bring you down if you start far away. If you start getting closer to the true minimum, you're going to have trouble converging. Okay, so this will have trouble converging. Let's write some of these points down. Okay, so SGD. So one is going to be fast, may not even look at all of the data. Okay, so this may be, the runtime might be sublinear, right? I don't even have to look at all the data in order to find the model. Like, it's got some randomness assumption. That's great, right? And it took constant time, to build the model for each data point for a constant size model. So it's really sublinear time, which is pretty cool. Okay, so you can prove. So you can prove what's called, so the quadratic convergence. That means I need roughly log 1 over roughly log 1 over epsilon steps, and I'm going to get to epsilon error. I can prove this under some conditions that are weaker than what I need for the batch gradient descent, but there's some ways you can prove this kind of it's randomness. However, there are some technical conditions here. So near the minimum, it's going to be more noisy. I mean, more noisy close to the minimum. And so this means that this is true up to a point. I'm going to get this quadratic convergence, basically, up to a point. And after that point, I can continue by maybe decreasing the learning rate or having a batch of things I look at once. And so there are ways to play with this. But this property tends to generalize better. Okay, so this is, yeah, I think this is, okay, there's one more important point I want to make, and then I'll come back and kind of rant on this a little bit beyond what we need to cover, but let me make one more point first. So I'll talk about that in a second, but this check of convergence also needs to be done a little bit more carefully. Again, because one data point might be noisy, I'm going to need to look at probably take the average over the last B updates. I'm going to set some parameter B and then look at, say, the last 10 or 20 updates and look at the average norm of the gradient instead of just the last one. Because the last one might happen to be very small for just one data point, but that doesn't mean I've actually converged. Or it could be it's really large for one data point, but on average it's small. So I kind of want to do this in a way that's I want to take an average. Okay, so this has kind of been observed in these really big models people have used in deep nets, but also other models where they use gradient descent in some form, that you don't necessarily want to be exactly at the minimum of this cost function that we've defined. The minimum, if you don't know any better, the minimum is probably pretty good. But if you think about it, if I'm close to the minimum, and when I look at an average or some data points, and I'm kind of sometimes increase my score, I'm sometimes hopping away from the minimum, well, that means that data point I looked at under this kind of PAC model, this probably approximate correct model, where I assume my data is IID, it's saying, in the cross-validation way of thinking about this, where I want this to generalize to new data. So this is the data point I'm seeing and I'm using to create my gradient, my estimation of the gradient, is kind of like an example of a data point I haven't seen yet. And so if I want it to be good on data sets I haven't seen yet, and sometimes those have a high score on the optimal model, the one that minimizes the cost function, then it says, well, I shouldn't trust the cost function that much, right? So if I'm not actually converging, that might be because, I shouldn't trust the model past that point. My data does not fit perfectly to that model. Sometimes it's larger, so what's the point of minimizing beyond it? Okay, and people have seen in practice that this tends to generalize to new data a bit better if I leave some noise at the bottom. It's not clear totally why you should have a worse sum of squared errors generalizes better, but if I start bouncing around, it tends to get me to positions that generalize a bit better. This has been observed empirically, and I think there's been some kind of ways people have proved something about it under some assumptions and so forth, and I don't know how much to entirely trust their assumptions, but I wouldn't, the point is not to be too worried about this. So just run it until the average kind of decreases below kind of the variance or something like that, and then you can kind of stop. Okay, so there has this issue, but not to worry about too much, and just run stochastic gradient descent. It's simpler, it's easier, or the incremental version probably works fine. If you're worried, randomize over your data. Okay, I have 1 minute left, and this is the last gradient descent talk. This is not quite what's actually used. There are these other tricks in gradient descent that we didn't cover in this class. You may see in the numerical optimization class, such as using like momentum or these second order methods, where instead of just looking at the gradient, I look at the second derivative of the Hessian, and this allows me at a very long and skinny function to kind of like transform it in ideas like we'll see in the PCA section, so it looks like it's round, and then the gradient descent works better. If the function is ill-conditioned in some way, then there are ways that these second-order methods can look better by looking at the second derivative. Now, these are much more expensive, and I can't quite do SGD by that. I need to kind of do these small batches. But there are these methods that go beyond this and kind of blend in these other tricks that we're not going to talk about. And these kind of really will work the best, but this has gotten you kind of 90% of the way there. Okay, and it would take several more lectures, I think, to really explain at this level how these other approaches work. But again, they're not too much more complicated than this. But the mathematics becomes more complicated than the intuition, and there's numerical analysis classes will go into more depth on this. Okay, great. So I will stop there and take questions, and then we'll start on dimensional reduction so next week.